Okay, I think I'm chairing the Astroph today. So I think it's get started. So who want to go first? Tomoki-san, you want to go first?
Okay, I will go. Okay, can you see my screen? Okay. Today, I would like to introduce this paper. This paper is regarding localization of FRB and its persistent radio source. And in this paper, they observe using VLBI in this paper, using European VLBI network, they observe this FRB. And in previous study, it is said that this FRB is located with persistent radio source. So in this paper, they confirm this association between this FRB and its persistent radio source. And they also argue some properties of these FRBs. They say that its host is low metallicity star forming dwarf galaxy, and its redshift is around this value. And they also measure the size of persistent radio source, and this is smaller than about 20 parsecs. And from observation of fast radio burst, they estimate the time evolution of their dispersion measures and rotation measures. And they find no evidence for they find no evidence for galaxy cluster on the line side of this FRB. So the evolution of dispersion measure and rotation measure may be due to its host properties. Okay, I think that's all from abstract, and I would like to show tables and figures in this paper. They observe this source for 58 hours, and they find 8 FRBs from this source. And for some burst, they measured rotation measure and rotation measures, and this value is discussed later. And at the same time, they observe persistent radio source. This persistent radio source is reported from previous study, maybe this study, but they say that the association between persistent radio source and FRB is weak in this paper, and they confirm that association. This is the image of persistent radio source here. And this dashed circle shows the result of previous studies. And okay, this may be the localization of burst, not persistent radio source, but observation burst itself. And maybe this figure is very important, I think. This black dashed vertical line shows persistent radio source. So from their observation, they know that persistent radio source is inside these lines. And they evaluated cumulative distribution of FRBs. They say that they use 5 combined bursts, and I don't know why they don't use all of them, but in this paper, they combine the raw data of 5 FRBs and localize the position of this burst. And this y-axis shows cumulative distributions, and it reaches about one well inside this black dashed line. It means the size of the localization of persistent radius source is larger than the position of FRB localizations. And so they claim that these FRBs are associated with this persistent radius source. It means it came from same position inside galaxies. Maybe this is one of the important results from their studies. And they also this is most important. And this is so redshift dispersion measure distribution of some FRBs. I think this is not new because I don't think this is new because we already know the FRBs and its dispersion measure, but just for illustration, I think they show this is redshift and this is dispersion measure, and this FRB located at here, so well beyond, say, these clusters. And they also discuss about galactic metallicity of galaxies. I think Shotaro-san is not here, so we can't ask him, but he may know much better than me regarding these parts. And they also compare, this is first, rotation measure evolution with other data. Panel figure shows this time evolution of rotation measures. And I think this green box shows the observed rotation measure in this study. And I think these rotation measures are consistent. These rotation measure values are consistent with other detected FRBs, maybe this gray circle or such kind of values. So regarding rotation measure evolution, they find nothing new, I think. Okay, that's all from this paper. And in summary, what they did is observe FRBs and confirm the association between persistent radial source and FRBs, something like this. This is main point of this paper, I think. Okay, that's all from me.
So, any question to Tomoki? No? Question? No? You don't have question? No. Okay, if there's no questions, thank you, Tomoki-san. So,
Okay, thank you very much.
Okay. Okay, next. Can we go next to Dora? Okay. I used it. can you go to? Okay, so I still have some problem with the laptop, so it's better to go to step first. So can you go maybe? Yes, I can move first. Yeah. Okay, thank you. Okay.
Okay, good afternoon, and I'm Stephanie. Today I'm going to present a news from Sky Tech Daily, and the title is If Aliens Are Looking for Us, This is How They Would Find Us. It's about a new study from Penn State and NASA's Jet Propulsion Laboratory, and the researchers want to find out how deep space communication might appear to extraterrestrial observers, and they analyzed NASA's Deep Space Network transmission to find out the answers. I think that this article remains two main questions. The first one is how outsiders might detect us, and the second is how to refine our own strategies in the search for extraterrestrial intelligence. For the first one, how outsiders might detect us. We know that humans communicate with the spacecraft and probes that we have sent to other planets like Mars, like the picture right-hand side. But the planet does not block the entire transmission, so a distant planet positioned along the path of these interplanetary communications could potentially detect the spillover. And the spillover means the green part of the picture. That would occur when Earth and another solar system planet align from their perspective. That is, they stay at the same line. So this suggests that we should look for alignment of planets outside of our solar system when searching for extraterrestrial communications. And the picture shows that we send a signal from Earth to Mars. Then, if a planet outside the solar system exists at the place, then the extraterrestrial intelligence of the planet might detect the signals we send from Earth. But what kind of transmission might be detected? The researchers think that we should focus specifically on deep space transmissions. For example, signals directed to interplanetary spacecraft and space-based telescopes, because they are strong enough to let outsiders detect. And we should not include signals intended for satellites in low Earth orbit, because they are much weaker and unlikely to be detected. So the researchers analyzed NASA's Deep Space Network. But what is NASA's Deep Space Network? It has 3 locations around the world. They are Goldstone, California, Madrid, Spain, and Canberra, Australia. Deep Space Network is very important because it provides the crucial link between Earth and its interplanetary missions, such like communicating with James Webb Space Telescope. Also, it sends some of humanity's strongest and most persistent radio signals into the space. The public logs of its transmission allowed the researchers to establish the temporal and spatial patterns of those transmissions for the past 20 years, so they can do the research. And they find out the chance that extraterrestrial intelligence would receive the spillover from the Earth under 3 different situations. For the first one, if the outsiders were in a location that could observe the alignment of Earth and Mars, then there are 77% chance to detect the spillover. And for the second, if they could view an alignment with another solar system planet, not Mars, then there are just 12% chance to detect the spillover. And the last one, if there's not any planet alignment, then the chance is very minuscule. So this is the answer that how might outsiders detect us. And for the second question, how to refine our own strategies in the search for extraterrestrial intelligence. We know that solar system is fairly flat like a plate, so researchers think that we should search within 5 degrees of Earth's orbital plane, and especially the planets that their plane is oriented with its edge toward Earth. What do researchers want to do next in the future? They want to identify these systems and quantify how frequently they could have received signals coming from Earth. Also, they are going to using deep space network to search for laser transmissions from exoplanets instead of radio waves, because they think that maybe outsiders use laser rather than radio waves. So this is the summary of the strategies. We should search for the black hole range. This is the range that we should focus on for finding the extraterrestrial civilization. That's all. Thank you.
Any questions? Aliens. Okay, any questions, Dora? Okay, you're good. But okay, I have one question. So it's a simple question. So the aliens here, it start from our Earth or from outside our Earth?
Earth.
Earth.
Where is
aliens? The aliens start from where?
From their planet.
And then if we want to see them, we need to search plus minus 5 degrees.
Yeah, because when all planets are at the same time, then it has more probability to detect the signals from each other.
Okay. So the plus minus 5 degrees is the range if you want to see aliens.
Because humans send signals from Earth to other planets usually, and other planets are on the same plate.
Okay.
So if we send to not on a plate, then it's not enough chance to.
Okay, I see. Last questions maybe. How if the aliens comes from very far distance?
Comes from
but it's too far from our solar system. How we can detect? Do you have? So actually, I also don't know how they, detect our life, right? Because if they are so far from our solar systems, maybe the signal have a delay or something. Yeah, it becomes so difficult to search alien.
It take a long time.
Yeah, but again, sometimes the detectors of our detectors is so it should be, clear enough, right? Because if too far, signal is too low. So how to differentiate this is the signal from radio or from aliens itself? We have to differentiate. Okay. Maybe. Okay. You have questions here.
I have a question, but what makes positive and negative 5 degrees the most optimal way to, like it says that it should be the range we should focus on. What makes it the most ideal?
Because the purpose of humans send signals to the space is want to sent to our planet, and our planet of the solar system are all on the same place. So that's why we had to just look for the place, because we send these signals. The purpose of we send these signals just want to detect our planet.
Yeah, because the planets is roughly in the same plane, right? So if you want to focus on one spot, the signal should be spread in a local point, right? So it's like you need to have a plus minus 5 degree. If you take too much, maybe the signal comes, I don't know, where it's not quite local. Yeah, it makes sense.
For the past, we might send signals. For the past, just send for the text.
Okay.
The data.
Okay. Thank you, Stephanie. It's interesting to find aliens. Okay. Thank you. If there's no questions, no. So thank you, Stephanie. And move to Dora. Can you share your screen? If you have some difficulty to this, can you send a link to me? I can help you to open the.
Links the papers.
I mean the link of the paper.
How I sent to you?
Yeah, just to the chat. So yeah.
So now it's okay. Today I'm going to present a paper is about gamma ray light and electron positron annihilation and possible radio emission in X-ray pulsars. And the accretion of the neutron star in X-ray pulsars, they will cause intense X-ray emission and will produce gamma ray in high energy nuclear interaction. So that's because the high free fall velocity of decreasing near the surface of neutron star. So in high magnetic field, gamma ray can produce electron-positron pairs. If there's annihilation of these pairs, they will produce second emission light at 511 keV. Okay. In this abstract. So gamma ray will be influenced by magnetic field strength and accretion luminosity and neutron star compactness.
You don't need to go into the details, just the important figures and
Okay.
yeah, just some other things.
And in this figure, there's two lines about 2.2 and 5.5 MeV. In beginning, in x-axis is the accretion luminosity increase here, and the gamma ray lines flux scale also increase. But when it comes to high max accretion rate here, so the radiative forces slow the accretion near the neutron star surface, so makes a sharp decrease here in high luminosity of X-ray. So let's move on to the figure 5. Oh, here. And this figure is about the fraction of photons that escape the magnetosphere of a neutron star, and the fraction of photons tend to drop with the increased value of surface magnetic field. So it means the higher energy gamma ray photons are more able to penetrate the magnetic surface here. So this y-axis is about total fraction of escaped photons, and x-axis is about magnetic field strength. So if they comes high value of this orange line is 67 MeV, so the gamma ray photons are more able to penetrate the magnetic surface. And can I zoom out the? Oh, okay. Okay, if you can see it clearly, next three figure is about different MeV values figure. I'm sorry. This is about 2.2 MeV and 511 keV, and sorry. And the left side is 5.5 MeV and 511 keV, and right side is 67.5 MeV and 511 keV. So in these three figures, when each high luminosity of X-ray in here, just the y-axis, gamma ray decrease, so it will be in dark color, like blue or purple color, like here. The higher X-ray luminosity here, and the gamma rays luminosity is decreased, so it's dark color. Also in 5.5 MeV and 67.5 MeV. So, and also in high magnetic field value in x-axis, the gamma ray is suppressed by magnetic field. Also in these three figures. So especially for 67.5 MeV, you can see the zone of low luminosity of gamma ray is more than the others. Like here is more big than 5.5 and 2.2. And these thresholds process this energetic collision of inelastic proton-proton collision. So for less massive neutron star, gamma ray and annihilation light luminosity will be lower or absent. So you can see the difference from 67.5 MeV with 5.5 and 2.2. So in conclusion, this paper provides some insight of gamma ray and annihilation in X-ray. So it will be useful for upcoming observation and research of gamma ray, just to know some influences. Maybe it will, just like I just say, maybe it will influence by the collision or some annihilation. So it will provide some parameter for the future work about gamma ray. Yes, thank you.
Okay. So, any questions? Okay. Hmm.
I still have no idea why the counterpart is not. That's yeah, the blue and the yellow. It's not.
Which one?
The right down.
This one?
Yes.
And you mean the continuous, like,
Is it just abrupt?
it's just like not like a curve like this one, right? So it's look like, you know, the edge is so, I don't know how to.
I'm not sure if it's about, it will be some related by 67.1, because I'm pretty sure why it looks like this. But, yes.
But what is the difference between the left and right figure 7 and 8? What is the difference? Because it's so, if you see in the figure 7 in the left and right, you go to panel 511 KeV, they are the same energy, right?
Yes.
But what is the difference between left and right?
It will through the 5.5 and to move on to 5.1, and also it will move from 67.5 and to 5.1. So if there's, we just know it, there's different from 5.5 and 67.5, because 67.5 have more sensitive by the photon-photon collision. So because of this effect, so makes the threshold more big than this one. So maybe because of this situation, so makes the 511 biggest different from each other.
So this paper actually, so this paper is like, you want to know what is the emissions from the X-ray pulsars, right?
Yes, and because of pulsar of X-ray, and it also produces the gamma ray. We also know some optical X-ray is also just like in different temperature, so it will also use gamma ray. And gamma ray will influence by the pulsar's magnetic field or something else.
Yeah, it makes sense, like, so, because, you know, in pulsars and magnetic fields there are plasma, right? So the plasma is plus and minus ion. So if they are collide to each other, it may induce the electron positron particle, and then they smash and annihilate, right? And after the annihilation, the photon will produce. So that's maybe the reasons why we can observe the photon outside this one. But if the magnetic field is so strong, maybe they haven't something to collide, right? So it will produce the different energy of a photon. So like in the previous, like in the previous graph, so there is a magnetic field versus luminosity, right? I think this one. You see? total fractions of escape photons, right? So I mean, if the magnetic, so all of the trend is if the magnetic field higher, so the fraction of photons is lower, right? It means that if the magnetic field higher, so the electron and positive ion, cannot collide to each other. So they have less chance to produce a photon. So it just look like, it's like here in the large field. But you see in the 67 MeV, right? The total fractions is less, right?
It's very low.
It's very low. I don't know why, but but 67 MeV is larger.
And this one is about as that photon. So
So the E here is the energy of a photon, right?
yes, and
Oh.
Y is about escape.
The number, right? The number of photons. But 67 MeV is the greater.
Yes, so lower energy photon escape easy.
Ah, yeah. So I think that's.
So it's about
Maybe, but because the higher energy, shorter wavelength. But I don't know the reasons. But actually, it can be imagined that if you have a charged particle in the magnetic field, so if they are so strong, they are so interactive, and then photon may absorb by another collisions. So there are some photons may escape lower in the high magnetic field. Yeah. I mean, not the annihilation lower, but so for example, if there is a photon from a magnetic field like this, so this photon should penetrate, right, to another plasma. So this photon may absorb by the another one, right? It's like if you have like a soup of ions, and then there are some of collide together, and this photon may absorb by the other electron, and the energy is lower and lower. Or they are so difficult to penetrate. Something like that, I think. I think it's like, in ray ionizations in cosmology. So when the first Big Bang come, and then they very hot, right? And then make a plasma, and then there is a photons productions there. And then the photons may absorb by atoms or something, right? So the photons may lower and lower. So that's why the universe is so cold, 2.7 K. I think it's a similar scenario this, but this is for pulsars, extra pulsars or something. I think. Yeah. Okay. Yeah, fine. It's just discussion. Okay, thank you, Dara, for explanation. Okay, it's about time, so thank you for the speakers today. Let's try to choose who wants to present tomorrow. Is there any volunteer? Who wants to present tomorrow? You? You want to present? Really? If you don't want, it's okay. Okay. So yeah. So and who else? No. No. Okay. Shout. You want to present? Not tomorrow. Okay. So we have Bea and who? Okay. You okay? Okay. Dora again. Okay. Thank you. And one more. You want to read news? But actually, you don't need to make a slides. It's okay. You just present in the page and give it a rough idea. You don't need to, give a detail like a presentation. Okay, but maybe next week. Next week. Okay. One more. What should be me? Okay, let me volunteer for myself tomorrow. Yeah. Okay, so me, Dora, and Bea tomorrow will present. Okay. Thank you all for your time. So let's close this Astroph today. Thank you. See you. There's nobody actually. Okay, thank you.